is there a fundamental science to be learned and maybe even some use cases in these very prototype kind of computers that are teaching us to make a future quantum computer? I mean, absolutely. Yes, there's a lot of room and a lot of things to do. And a lot of those things are not so much about quantum, they're actually about re-envisioning classical computing.
While we await practical business advantage with quantum computing, has QIS already furthered our understanding of science? What's the difference between a simulator and emulator? And how does a physical quantum computer fit in? We explore everything from tensor networks to thermodynamics to complexity, with an eye to how the hardware timeline will make practical power a reality in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is a professor of physics and quantum engineering at Colorado School of Mines, Lincoln Carr. Welcome to the show.
Hi, so nice to be here.
Yeah, thanks so much for joining. A lot of quantum information science discussions tend to focus on future use cases, which are important to prepare for. But QIS might be already teaching us a lot about science. So we're hopefully going to get some current things too out of this session here. But let's dive in a little bit here right now with something a little more general that'll help the audience get oriented. When we talk about quantum computers, then we also talk about simulators and emulators. Do you feel any need to differentiate those terms maybe a little bit? Throw a stake in the qubit, as it were, about whether we need to change the meaning of these terms or if any of them mean anything specific to you in this
Sure.
concept?
Yeah. Well, if you're a computer science person, you want to use the word emulator.
Mm-hmm.
But we commonly use this word incorrectly, simulator. So simulator generally in the computer science world would be something that's on a classical computer. And an emulator is like a wind tunnel. Instead of simulating a wind tunnel, you put your airplane in the wind tunnel and you run the wind over it and see what happens, right? So actually all quantum computers are emulators right now. None of them are actually computers because it's not error corrected. This is a little bit complicated because right now, as you may be aware, classical computing, the stuff that's supporting our conversation, in fact, is hitting a wall. The data centers are running out of room because of generative AI, among other major impact factors. And so we have to reinvent computing itself. So we're in the middle of reinventing even what we mean by a computer, which is very exciting. And so quantum emulators, or what we casually call computers, have a major role in that reinvention.
Yeah, that makes a lot of sense. And what would you say that using emulation has already shown us?
Okay, so this story starts in 2002 with two major results. So it's been going a long time, 22 years now. And the two major results are the following. One was done, by the way, by a master's student who's now a professor at Harvard, Marcus Greiner. And the other was done by some really outstanding people at Gila right here in Colorado. So one of them is how do bosons become fermions? So these are the two kinds of particles in the universe. Our body is made of fermions, protons, electrons, neutrons, right? That's what makes up our body. And those are qubits, by the way. They're non-binary. Our body is built of non-binary things. So fermions are exclusive. They don't like to be in the same state. They're sort of like cars. You put two cars in the same place, bad things happen, right? And then bosons are like, a crowd of people at a Greek party in Boulder. They all want to be in the same house, and it gets impossibly full, and then yet more pile in. So, that's what makes lasers work. So photons, light is a boson. So now it turns out, fermions can pair to make bosons. It sounds a little bit technical, but that's what's actually underneath superconductivity, which is the big dream, for quantum computing, that will understand superconductivity, for example. And we didn't really know how fermions pair to become bosons gradually. We know that happens in matter, but this was an unknown thing. So how does one basic kind of particle in the universe turn to the other kind of particle? This was unsolved until this project came along in 2002. And through these quantum emulators, they were able to solve that problem by causing this pairing to occur very gradually and really discovering something totally new about the universe. And so that's one of the things that quantum emulators are doing. They're teaching us basic things about the universe, like how does one kind of particle become the other. So that's a big result. And the other one done by originally this master's student, I love this story because I like to encourage young students. We have a great quantum engineering program at Mines, and we have a lot of master's students in it. And I like to tell them, hey, a master's student actually started your whole field. and that's that problem was, imagine if you froze, water into ice, and then you had such incredible time resolution that you could watch it oscillate from water to ice to water to ice. Imagine if you saw it, melt and refreeze and melt and refreeze. Now that's something hard to imagine with water and ice, but in fact it happens in quantum matter all the time because of quantum fluctuations. And this master student was able to show that that matter in a crystal of light would do that. And that is called a dynamics of phase transitions. Okay, and so that was discovered, understood, observed. It's still an ongoing field. It's been going for 20 something years, and it's changed how we think about the basic building block of STEM called thermodynamics. So that's a huge scientific discovery. So both of those things are absolutely fundamental science. Started 22 years ago, continue, and have really blown up because of the new capabilities in what they call now quantum computers, like they have at Google and IBM and Quantinuum, et cetera. So, yeah.
So to do that level of work, what would be required? How many, fake qubits, if you will? Like, what would you need to do something like that now?
Okay, so there's many different kinds of quantum matter, and qubits is only one example. Of course, it's the one that's best known in the press. And I would argue the reason it's best known is because we love to take the thing we know and just put the word quantum in front of it, right? So if you take bits, quantum bits, you do gates, quantum gates, computers, quantum computers, it's very convenient to take the thing we know and just add, turn quantum into an adjective, right?
Yeah, or unfortunately shampoo or, vitamins or whatever. Yeah.
Let's not forget quantum healing, right? So there's a lot of great examples, and some of them are inspirational, like quantum healing for people, which I think is great. I mean, metaphor is great. On the other hand, that's not tech, right? And so this quantum computing thing can be a little misleading because, in fact, there are many kinds of quantum elements that come together to do a quantum task. And those elements could be bits. They could be what are called qubits, which are much larger quantum spaces. They could be continuous variables. We can sort of think of them as like pulses of light, for example. And all of those can come together to create a quantum result. And so those early quantum emulators, they didn't use quantum bits at all, right? They used something that was continuous. So you imagine that you have some matter over here, you have some matter over there, right? And then this matter can interact in different ways, and that interaction is modulated by the presence of this crystal of light, and that's what allows you to go through, say, a phase transition and see, by analogy, water oscillate into ice back into water. Okay, so, and this is literally quantum liquid and solid, by the way. It's the quantum analog of this, but I didn't call it quantum water and quantum ice because I don't want to do the same thing everyone else is doing. So I would love to give you some quantum tea, but I don't have any to offer over this podcast.
Okay, so back in 2021, you worked on paper, Quantum Simulators, Architectures and Opportunities.
Yep.
And it talked about, and it used the word simulator, of course,
I did.
and it talked about like 300 quantum simulators in operation worldwide, which has obviously grown since then.
Right.
So how does that differentiate from what you were just talking about?
Oh no, those are early quantum simulators, or emulators, and they have become quantum computers now. The idea of a quantum computer is it's much closer to a classical computer. You have discrete operations that happen in circuit layers. So from the physics perspective, we would say it's an interacting quantum system that is discrete in space and time and has local operations. Okay, and those local operations are the gates. Like you can think of like a NOT gate, like true, not true, or an OR gate, or an XOR gate, or an AND gate. So those are kind of the building blocks of classical computers. And they, for the general listener, those are nothing more than addition and multiplication. Like 1 + 1 versus 1 × 1. So it's like an OR versus an AND. Okay, so it's these operations are fancy names for what everybody does in, like, I don't know, probably first grade, and probably all human beings on Earth do naturally in their brains. And probably also crows and dolphins and lots of other species. So I think that kind of idea, it's so simple. It would be great if we can kind of turn that into a quantum device and make it do everything. That might not be true, but we're trying very hard. Yeah. And those devices, they allow a kind of control over those gates, over those local operations that we did not have before. Before we did a thing to the whole system, we watched it evolve. We did another thing, we watched it evolve. Now we can like get in and locally do something. It's like if I could, I don't know, go in and I could reroute roads, one by one, rather than saying, hey, don't too many people come to the city today, and then see what happens, right? But imagine if I could go in with little, barriers and really create a different path through the city. That could be a really effective way to deal with traffic, rather than just saying, oh, less cars on the road today. Yeah.
And that's a good point. Is there a way to extrapolate some of these approaches to more like everyday kind of use cases, like the ones that people are dreaming about? Like you brought up the example of traffic, for example, like an
Sure.
optimization and things like what have we learned from this basic approach to more real world uses?
Okay, well, in my opinion, it's my personal
Hmm.
opinion, but many people would agree with me. The most important outcome of quantum computers so far is to re-envision thermodynamics. And that might sound abstract, but thermodynamics is what makes engines work.
Hmm.
Okay, think about cars, right? They all run off engines. Our whole society, power generation, it all deals with some kind of information transfer or heat transfer, energy transfer. That's all thermodynamics. Thermodynamics is the energy grid. Thermodynamics is our power grid. Ideas in thermodynamics are applied to understand human interactions and social outcomes now in what's called statistical physics. So, like all of those ideas, if you're rewriting those fundamental ideas, you're rewriting the possibilities of tech. And I'll give you an example. You imagine that you have a working fluid of an engine, and usually you think of, like, I don't know, gas, and you imagine heat and things like that, like in your car, right? Imagine if your working fluid is pure information, right? That's a whole different concept of an engine. And so these devices are exploring, for example, engines that use information as a working fluid. So of course they're very small, but when we think about nano devices, in science fiction, there's always these nanobots that take over the world. Well, hopefully they won't take over the world. Hopefully they do some good things. But if we want to make devices like that, for example, for medical purposes, to have individualized medicine, we need to understand the working principles of those devices. And so those quantum computers, the most important thing they do is not that they solve traffic problems, like maybe one day they will, but what they're doing right now is they're rewriting the basic laws of thermodynamics, right, at the small scale. So that's a really big outcome. And keep in mind, classical computers, they cannot go forward without understanding that. So we cannot go forward with computing at all, and our whole society runs off computing. So I think it's fair to say that quantum computers are essential to the future of humanity, not in the sense of breaking all plausible encryption or being super fast, super powerful computers. Maybe one day, not clear yet, actually. But what they really are doing is they're rewriting the rest of things. Yeah.
Okay. And they're not rewriting the second law of thermodynamics, right? Because there's going to be a big problem if that happens.
Okay. Right. So second law of thermodynamics. Okay. So now the second law of thermodynamics involves entropy,
Hmm.
and entropy is a classical concept. So when you talk about quantum entropy, actually it behaves very differently. And so already the second law of thermodynamics is modified in some sense at a very small level. One of the major discoveries has been this is related to what's called the Maxwell's demon problem.
Hmm.
If perhaps listeners have heard of it, it's a fun thing to read about. And besides that, has the word demon in it. So it's exciting, right? So, but, Maxwell had this idea that you could somehow overcome, thermodynamics if you had someone making some choices somewhere along the line with information transfer. And that was the demon. Okay. And it turns out that, through this kind of quantum investigations, we've come to understand that there's a cost for information creation and for information erasure. And the joint cost of information creation and erasure balances the information equation and allows us to solve these tiny information problems like this information-based engine. Okay, so without that fundamental understanding, we couldn't move forward. That's not contained within the second law of thermodynamics in the obvious way. So
Yeah, it was
yeah,
flawed from the get-go. People back then didn't realize that little demon sitting there had to know when to open the door to move one particle to the other side.
and he has to forget things,
And
and
yes, they
forgetting
forget
costs.
exactly. Yeah.
Which is so interesting. We think of
Yeah.
forgetting it as a loss, but it actually costs, right? And so that it's actually my colleague Masutu Ueda, who is one of the real people that solved this problem. There's a few around the world, but I really like to relate to his work, and he has really good papers on this. He's a super prominent guy in Japan at University of Tokyo. He's an excellent communicator. I can highly recommend his work. Whether you see his talks online or you read one of his papers, and his English is excellent, which helps. But he's just really good, clear thinker, and I think solving problems like that is one of the reasons that this foray into quantum computing has really changed changed humanity permanently. It is a real next stage in tech.
So, how do you feel about continuing forward with using machines that aren't full-fledged quantum computers? Do you feel like there's still a whole unforeseen evolution to these types of machines that we haven't even thought of? Like we have roadmaps for how many qubits are going to be in a more traditional quantum computer,
Right.
but do you think there are like maybe still engineering tricks and even software tricks on the horizon for getting more out of like classical emulation of quantum? Like do you feel like there's something there that's still untapped that maybe we should be looking at?
Well, I'm going to first refer to the general situation we're in, which is the Hitchhiker's Guide to the Galaxy situation, right? And that's that we're building the computer to teach us how to build the next computer. Okay.
Yeah.
So it's the computer to make the computer to make the computer to make the computer, which then does the thing. And
Mhm.
so a lot of this is early prototyping. That's very typical with early prototyping that you do this, what we call lower technology readiness levels. So is there like fundamental science to be learned, and maybe even some use cases in these very prototype kind of computers that are teaching us to make a future quantum computer? I mean, absolutely, yes. There's a lot of room and a lot of things to do, and a lot of those things are not so much about quantum; they're actually about re-envisioning classical computing. For example, to make a quantum computer work right now, you cannot just program something and launch the program. So, I mean, I worked with Google. I was one of their early access users on their machine. And I can tell you, I had beautiful theories that took into account all the noise and all the lack of error correction and all that, and really good equations. And, when I ran my simulation on the Google's quantum computer, the first thing I saw was just flop. This is like nothing, and that's because the real computer doesn't really do what our models do, right? It has a lot of other factors in it you have to take into account. And in that paper, which was on, not to plug my own work, just to give a reference here, that paper is on quantum cellular automata. So that's about creating what are called small world networks and entangled complexity. And small world networks are like, I don't know, like airport networks, for example, or the internet or the brain, right? So they're very typical. So to show that they occurred in quantum systems. So to make that thing work for the first time on a quantum system, I have like 6 or 7 major corrections that have to happen that were not my original theories. And it took a year and a half instead of 3 months, which is what I naively thought would happen. So that is because you're not really just programming with software. That's my model, right? In my code, you're programming every part of the quantum computer from the top down to the bottom. So they call it the computing stack.
Mhm.
So like the bottom is the actual chip and the control of the chip and the material of the chip, right? And how you interface with that material. And then you have, all of these layers between. Some of them are hardware, some of them are hardware blended with software, and some of them are really different abstraction layers of software. So full stack programming is the only way to program a quantum computer. It will not work otherwise. Classical computers, we had so much room. It's very rare you think about full stack coding, but because we're running out of energy and memory and bandwidth for computers, right? We absolutely have to start doing full stack computing. So quantum computers are helping us to really think about full stack computing and how
Yeah,
to run at every point of the stack. Yeah.
there was just a paper published about something like that with classical, where you're doing more parallel processing in the separate cores of the same task, and they were getting up to a 1.9x improvement in performance or something like that. Still a lot to be figured out there on how well that'll work. But yeah, it's very similar. It's going right down to that level, and it's a whole new stack approach
That's
to
right.
how they're going parallel. Yeah,
Exactly.
seeing
And
lots
there
of
are many
that.
such innovations in quantum computing that impact classical computing directly. Whether it's photonic computers or so-called Shannon computers that are probabilistic, right? Or it's reversible computing. You can run a superconducting quantum computer cold enough so it doesn't create more entropy. Speaking of second law, so the change in entropy is zero. Okay, so that's called
Mhm.
reversible computing. But on the other hand, not so cold that you have to make it be quantum, and it's already quite useful, right? So there are many, many kind of interfaces between those different architectures referring to my paper earlier, right, and the re-envisioning of classical computing.
Yeah, I was going to ask you about it in a moment, but we could dive into it right now and then switch gears back. So that's the small world effect for interferometer networks, right? That paper.
Oh,
Um,
I was just referring to the one that you'd asked about. That was a roadmap on simulator architectures. But
yeah.
in my personal paper that I did with the Global Quantum AI team and my colleague Elliot Caput, and a fantastic team of students who were obviously key to its success, that is on small world networks. That's right, and that uses quantum cellular automata, which is a really fun area. When I was a kid, these cellular automata were called Conway's Game of Life,
Hmm.
and with just flipping a few squares from black to white in a little grid, sort of like a checkerboard or something, you would see these incredible, beautiful living patterns emerge, and that's one of the ways they got kids into coding. So they would do that, and they would do fractals. You'd see like the Julia set or something, and then kids would be like, "I want to code for a living," So I got sucked in through those exciting examples. I still work on fractals and chaos, and I still work on cellular automata. So science communication works. Yeah, that's the moral of that one.
Yeah, that's a great example. And I've seen some quantum game of life simulations. There was a display in New York City here where I live, and they were doing different things like music and stuff, and one of them was like a quantum game of life.
Cool.
So just to explain it to listeners real quick, it's this idea that there are rules, like when you have two cells next to each other, what that means, whether they live, they die, and then after a while, you start to get complex patterns that emerge, and then they got their own names, right? Like people started naming these patterns that would emerge from the system. So how does that apply to how does that complex network theory idea apply to what you did on the Google machine?
Okay, and so to mention what those patterns look like for listeners who've ever been to an EDM show, you see them all the time because a lot of those kinds of patterns, whether continuous or discrete, as you just described, they're used to create the beautiful graphics that enhance your experience of the music. So yeah, they're really common. And then you asked how that relates to small world networks. Well, small world networks are a form of complexity, and in particular, this is pretty cool. People don't really ask themselves this. They take it for granted that if they want to get anywhere in the world, they only have to change flights maybe twice, right? But if you actually connected airports at random, you would change flights, like 30 times. Like it'd be really bad.
So yeah, if you just
right,
yeah, where are you going to find the next plane?
Yeah, you would just, and that's what happened early on, right? Because there weren't major airports, so you would just go from airport to airport, and like to get across the U.S., you'd sort of do this, these barnstorming, flights, where you land in fields and you get on the next plane, and it's similar for switching horses historically, it was really time consuming. But then you had big stables, so there'd always be a guaranteed horse, and so that idea that you've got hubs, and that those hubs allow you to shortcut paths from one place to another, that's one of the main concepts in a small world network. Of course, the internet does that. Biology does that throughout the body, and the many, many biological codes, including, DNA, but many other kinds of codes in the body, immune system, et cetera, right? There are many kinds of small world networks throughout our body. And then in the brain, the brain really uses this a lot. So the idea was through very simple local rules. Remember earlier I was talking about those local gates and local access and how that's been a real sea change from those early quantum emulators to what we currently call quantum computers, which are sort of pulsed quantum emulators with local access. So those current quantum computers, they allow us to create these local rules, and those local rules can then give rise to this global kind of connectivity. And that idea that simple local rules give rise to global features that are common between human social interactions, the brain, DNA, is pretty remarkable, right? To see that in a quantum system. So the reason I did that work is because at the time people were saying, oh, quantum systems are too simple. They can't give rise to that kind of complexity. And I want to show that they absolutely can. And it's the same kind of complexity as we're thinking with right now, And that's important because we actually don't know where that kind of complexity comes from. There isn't any theory of physics that gives rise to it. We have to kind of cook it up. And yet it's literally everywhere. So sometimes people think it's a missing principle, like gravity, it's like some missing principle. They call it like the complexity principle. Or sometimes people think it might be a reinterpretation, a new understanding of this principles we already have. And either way, I want to show that quantum has to be involved, that it's not a purely kind of classical or large scale phenomenon, which is what people had as a whole believed up till now. So part of my personal career, not to get too much in my own stuff, because this I think should be about general communication here, but part of my personal thrust of my research has been to show that every feature of classical and biological complexity you can find in quantum systems, and has nothing to do with living beings or large scale, or it's nothing like that. It's a basic principle of the universe. So in some sense, you can say that the universe is doing something like cognition, right? Something like the connectivity between airports, something like DNA. It's doing that at many levels all the time. And we notice the living level because, we're living beings. That's what we like to focus on. We think living things are beautiful, right? But in fact, the universe does that everywhere.
So do you think that kind of approach and learning would lead to quantum systems influencing other systems? For example, maybe in machine learning or something like that? Do you hope for any kind of crossover there?
Yes. And we don't even know what kinds of complexity arise in quantum systems because the whole field is so new. We didn't have devices that allowed us to look at things like that until recently. That's the beauty of these quantum computers. And yeah, we might not get like breaking Shor's algorithm and breaking all encryption worldwide and, hacking into government databases and like all the things people imagine that, quantum computers are going to do. And yeah, they might do that one day. In fact, I think it's even likely that they will. But right now, we can explore these basic principles. And, that's what people do with computers at first. Computers weren't, first used for EDM shows, right? First computers were used to, look at basic things like I have a bunch of springs and masses and they're on a grid and I pluck the system, imagine like like a piano string or a guitar string, but now imagine that they're in a square grid. And now I pluck this grid and I ask, do I have a memory of my initial plucking? It's about memory in a system like that. And one of the very first things people do with classical computers, in fact, I mentioned fermions earlier. Fermi himself, as a much older person, was involved with this. It's called a Fermi-Pasta-Ulam recurrence. And it was one of the first scientific calculations done with a computer, right? In maybe the 60s, 70s. And they found out when they plucked this grid that it didn't spread out, that it actually recurred, and it recurred like crazy in this giant, kind of pulse. And they discovered a whole new kind of physics that did not involve new principles, but was a reinterpretation of what we already had, and it could not have been discovered, right, without the classical computers. Then later we developed the math to support it and all that. And why does that matter? I'll give you an example. It turns out that in the ocean, every once in a while, an oil platform gets just shattered, just broken in half by a giant wave called a rogue wave. Okay, and a rogue wave is related very much to those early computational experiments of Fermi, Pasta, and Ulam, to understand that little waves all over the ocean can conspire to suddenly create this massive wave that has nothing to do with a storm that will just break your ship or your oil platform or whatever in half. And how do you plan for them, and how do you understand them? And those things occur in all kinds of physical systems, including the brain. Okay, so that basic principle in that early computation really does matter down the line, but it might take decades for that understanding to really play out. So people would love for quantum computers to solve the rogue wave problem or some other kind of problem right now. But in fact, quantum computers are more at the stage of, I pluck a grid of strings and what happens? That's pretty much what we're doing. Yeah.
Like when I think of emergence and complexity, I'm worried about things like, I don't know, is there possible for machine consciousness or something? Right. I would think someone standing on an oil platform has a more immediate concern when it comes to emergence.
Yeah. I totally
so there's a potential for quantum to impact all of this. Yeah, that's terrific. So to touch a little bit again on emulating these machines, I know you worked with Tensor Networks in the past. Uh-huh. It was quite a while ago. And are you still active in that? Are you seeing any of those approaches bearing fruit? Because I found that the world of classical computing still protects this sort of like 50 qubit barrier. It's kind of weird, right? Like you try to simulate 50 qubits on a laptop, on a supercomputer or something. And then of course, every time you add a qubit, you double the resources. It becomes impossible to get too big there. And then with Tensor Networks, you can put as many qubits as you want, but then you'd have to contract the giant mess that you create in the end. And then again, hardware seems to choke. So did you have any thoughts about that? Do you think there's anything there, or are we going to hit the same limits possibly?
You're asking the right guy, because my group supported the open source code for Tensor Networks used worldwide for about 15 years. So we put it down because industry is doing a great job at it, and I don't really need to compete with teams of several hundred well-funded people. I can go off and do other things, which is great because I really did it as a service. So now I can set that service down and let other people carry it on. But I do still watch the field closely, and I've worked a lot in it. I've done thousands of tensor network simulations. So tensor networks are the idea that quantum mechanics is a big matrix problem, which for listeners who don't know what a matrix is, that is just like a rack of numbers. You can kind of imagine you have a box, you have a grid on the box, and every point in the grid, there's a number. And by the way, every photograph is in fact a matrix because the values of the pixels are in a grid, right? And so, every video, every picture, that's a matrix. So matrices are really common.
Color mixes, things like that.
Yeah, exactly. Like when I teach my students matrices, I have them work with their selfie. So literally, like what are the mathematical properties of their face? It's a lot of fun.
I'll keep them interested.
Exactly, right? I mean, so matrices are very approachable. So now, the problem with quantum is the matrices get too big, right? And that's the beauty about quantum, is that they can deal with very big matrices, and like machine learning on images or video, right? That's the hope with quantum, and certainly very large matrices in general. That's kind of one of the big computational problems. So now it's possible to write this giant matrix as a product of much smaller matrices. So you can imagine in a face, right, a selfie, that you wrote your matrix as a product of a nose times an ear times a shoulder times a shirt collar, right? Now, that product might give you something pretty mixed up in the end, or it might be that you only need a few small matrices to make up an image, okay? And that's sort of about the information content of a matrix. And so that is called compression. It's information compression. And what you're doing is you're taking that giant matrix and writing it as a product over a lot of little matrices, so you're compressing the amount of information you need to support your selfie, right? So classical computers do that, right? They take a big quantum matrix, and then they try to write it as a product of a lot of smaller matrices. And that sometimes works and it sometimes doesn't. So for example, you actually can't do that in white noise. right? So if I took a selfie and then I randomized it till it looked like an old TV screen from my childhood, I'm old enough where, I actually did see black and white TV screens that, looked like something in the Twilight Zone and were just, just sort of white noise. And so if you try to do that, that's called a random state. So if you try to do that and you write that as a tensor network, only in some special cases is that possible. In general, it's not possible, right? So, and then there are things that have only a little bit of structure, and they're also very hard to write that way. And then there are things that are super structured. For an example, if I had just a grid of boxes, it would be sort of obvious that I could write it as a product over some kind of something that tells me to write boxes, and it would be easy, right? So sometimes that's called algorithmic compression or information compression. But the idea is that you need only a small amount of code to produce this very big, complicated thing. So what you're referring to is this kind of neck and neck race between methods like that related to tensor networks. And there are many, because people are very smart and they're all working on this right now.
Yeah,
and
the contraction problem.
Like I said, it's amazing. So yeah, it's going really fast. So they think a lot about information compression methods like that and whether that can be used to beat a quantum computer. So why does that matter? Because you're improving classical algorithms. So the number one effect of quantum computers on classical computers is to make the classical computers better, especially the algorithms. What I've been arguing throughout this podcast is that it's also going to improve the hardware. That hasn't really happened yet, but I think it's coming very soon. But it's certainly improved the software, the algorithms already. Now, can a classical algorithm always beat a quantum computer at the 50 qubit level? No, definitely not right now. And it's easy to write down cases where that's not true, but just a lot of times they're not the interesting cases. So the big question is, what are the interesting cases? Interesting meaning, I don't know, I mentioned a wind tunnel a while ago. If I want to understand something like how an airplane flies, if I want to make a better airplane, right? That's solving what are called Navier-Stokes equations. So if I want to solve Navier-Stokes equations, the equations for fluid dynamics, there's an X prize, right, for this problem. So if I can solve that with a quantum computer more efficiently, then everybody's going to buy the quantum computers, I can tell you, right? But right now, most of our cases are sort of weird cases. They're not really cases that matter physically for applications like that. They're more kind of mathematical cases or computer science cases that are very theoretical. Yep.
Yeah, absolutely. Yeah, I do a lot with tensor networks too. So,
okay, great.
I'd like to hear your take on it. Yeah.
So, all right. Well, I'm saying this for the general audience. I hope I wasn't.
Yeah, of course. Well, yeah, I often ask questions I know the answer to just so people can hear it from someone else but me. Yeah, absolutely. That's terrific. Yeah, and I do think they have a lot of potential to solve problems now, especially in the areas of compression, of course, things like SVD, other approaches. We can make things much smaller, and especially with edge cases and edge computing.
Right.
So before I let you go, I know you were involved with NIST for like 20 years. I just wanted to get your take on what you did there. Was any of it involving cryptography? Or was it purely just more on the like R&D of developing systems kind of approach?
Okay, so I actually want to give a plug for national labs here because I actually worked at 4 national labs in the U.S. and then also at CERN. And I think those kinds of environments are fantastic places to get science done. And so it was really my privilege to work at NIST. I was a NIST associate, so I was out there like in summers, and then continued to collaborate. So it's not like I was in NIST Central. Okay, so to clarify, yeah. But I really like NIST, and at some point I had a job offer there, and I honestly settled for family reasons in Colorado, but I still feel closely connected. And we have the mothership is out in Gaithersburg, but we have, a little spaceship out here in Boulder, which has, a few Nobel Prizes. It's a pretty powerful little spaceship with NIST Boulder. So I get to go over there sometimes. So NIST does a lot of fantastic things in quantum, from hardware to software, from cryptography to standards. And, the part that I was involved with is very much in the area of quantum emulators, right? And then the originator of my tensor network code is there was a code at NIST that was created by one of the absolute, lifelong experts and early inventors of computational physics, Barry Schneider. And then that little code sort of propagated its way into a slightly larger group of Charles Clark. And then they really didn't want to maintain it. And so then I took that code and I rewrote it, made it very big. And, with their agreement and support, turned that into what's called matrix product operator and matrix product density operator codes for the technical listeners out there. So those MPO, MPDO codes are what eventually went into my open source code. And those codes, they also do long range problems. And again, this is a bit technical, but I talked about those local rules. If you're working with solid state elements that go into a chip, then it makes sense that their crosstalk is fairly low. Like a piece of your chip, far on the left is not typically talking to a piece of the chip far on the right. Okay. But if you're working with the building blocks of nature, atoms, ions, photons, those things tend to talk very long distance, right? Because of electromagnetism. One way to understand that is like, if you think about, radio waves, they're kind of everywhere, or microwaves, like for your phone, they're kind of everywhere. And so electromagnetic things, spread out. And typically they spread out more or less like 1 over the distance squared. And if you remember something like how a sphere grows, the surface of a sphere, for those people who may unfortunately recall their high school geometry class. That was my favorite class, but for a lot of people it was not their favorite class, I can tell you. So, you might remember that there's this, 4 pi r squared, right, for the surface of a sphere. So that r squared, that's telling you how those things are growing. So that means they're very long range. So solving those kind of long range problems is very tricky with those tensor network methods, because before, I wouldn't think about my ear and my nose as being, close to each other per se in a face. But if somehow my ear and my nose are interacting, which actually does happen sometimes, right? It can be very uncomfortable. then you get these kind of long range effects. And so those codes were designed to do long range effects and deal with what are called open quantum systems interacting with an environment, and deal with going from states to operators, which is a little bit technical. But anyway, so that was one of the big things I did at NIST. And the other thing I did is I worked a lot on solitons. And solitons are like those rogue wave examples that I gave. In fact, they're everywhere. It's the number one thing you see when you look down, on the Earth, like with Google Maps, and you look at the oceans. You'll see these waves that look like sort of lumps or humps that are moving around on the surface of the ocean. So those are solitons. Yeah.
Yeah, that has a real game of life feel to it. This thing that just emerges and moves around on its own. Yeah.
Yeah, exactly. And so NIST was a great place to do those kinds of things. I worked with lots of people there over the years, and I continue to collaborate with them. Also in my government position, I worked a lot with NIST around standards and national standards and international standards for post-quantum encryption. And I can't emphasize enough how much people there give to the country, actually.
Yeah, and right now, as I mentioned, we're with the post-quantum cryptography aspect. They're taking on a pretty difficult concept there too, how to get everyone to migrate over. So yes, absolutely,
right.
Super important. And with that, I feel like I could talk to you all day, but we'll have to make a point to stop eventually. So yeah, thanks for coming on, and I know you've written lots of other interesting papers too, and you've talked about things like importance of universities creating undergraduate programs for quantum and everything. Uh-huh. And if I could just have one last thought from you, what are maybe 2 or 3 things real quick that universities listening should be considering for training their future quantum workforce?
Well, there are 6 pillars to the National Quantum Initiative, and 5 out of 6 are a big success, and 1 is lagging, and that is the workforce piece, unfortunately. So I think when you think about workforce, it's about educating the general citizen, actually. It's not just about educating toward a job. Educating people for careers, for 20-year careers, and not forgetting just their first job. I think that's what matters. So when you think about quantum workforce, imagine, you have to educate people for the entire future of computing. You have to educate people to be able to talk to our legislators and our dedicated civil servants and our CEOs and our artists and writers. And how do you create a person who can not only solve a quantum problem, but will be able to be flexible and adaptable in this rapidly changing landscape over the next couple of decades. And so that's a big educational problem, and it's one that we have some hints of how to solve, but there's a lot of innovation still needed to do that properly. It's really about the future of engineering, actually, not only quantum. So yeah, and that's something I work on a lot. And if folks would like to ask me about it, I'm happy to address those things. Feel free to reach out to me.
Great, thanks. And your info will be in the show notes. And thanks so much for coming on.
All right, thanks.
Now it's time for Coherence, the Quantum Executive Summary, where I take a moment to highlight some of the business impacts we discussed today, in case things got too nerdy at times. Let's recap. In computer science, a simulator or simulation typically runs on a classical computer. An emulator or emulation acts like a copy of something. You can simulate winds on a computer program and have a simulated plane fly through them. You can also emulate winds by building a wind tunnel and having a small physical model plane experience the airflow. Except for rare experiments, quantum computers are not currently error corrected. This means NIST machines are a type of emulator that tries to act like perfect qubits and gates. Lincoln says we're still building quantum computers that will teach us how to build better quantum computers, in a sense. Quantum simulations and emulations have already taught us much about science. About 20 years ago, ultra-cold experiments showed how sociable bosons could act like solitary fermions. We also learned about the dynamics of phase transitions at ultra-cold temperatures. Think water to ice and back, but far colder. We've also expanded our knowledge of thermodynamics, which can be applied to information. For example, fluids in a car engine behave a certain way with heat. Information can be that fluid. This isn't a new concept. The Maxwells demon thought experiment showed that a mythical being can decide which particles of gas pass to one side or another of a system, thereby decreasing entropy. This turned out to be incorrect because the information learned and forgotten by the demon is part of the thermodynamic system. Entropy still increases, and the second law of thermodynamics is protected. Complexity is a major area of Lincoln's interest. Anyone who has seen Conway's Game of Life knows about emerging patterns that appear out of relatively simple rules. In the real world, things like solitons or rogue waves in the ocean are potentially deadly examples. The hope is quantum computing will help predict these anomalies. He's also working on smaller networks or interactions that could affect code down the quantum stack. Lincoln has created numerous tensor networks as part of his work. These are ways of handling large matrices of numbers and the math between them, such as dot operations. These are popular for types of compression, but can also be used to simulate quantum gates on a classical computer. Such approaches have already improved algorithms and software, and may help improve quantum hardware in the future. In fact, if there's one point to leave you with, it's that most of the discoveries you heard about that seem science only in this episode could have real-world implications in practical applications as we build towards our fault-tolerant quantum systems of the future. That does it for this episode. Thanks to Lincoln Carr for joining to discuss his work. And thank you for listening. If you enjoyed the show, please subscribe to Protiviti's The Post-Quantum World, and maybe leave a review to help others find us. Be sure to follow me on all socials at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protiviti. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protiviti.com or follow Protiviti Tech on Twitter and LinkedIn. Until next time, be kind and stay quantum curious.